There is a last example that I would like to cover, is a three-phase system, still the MMC, and without delays to make things easier for this last example. I close the files that I do not need anymore. This one I need it because I'm working still with an MMC instance, but I would like to open all the other files, so I just do this and then F9, and then I have the files as before. Oh, apologies, so actually I have to run this before, otherwise the system still thinks that I'm working with the single phase MMC with delays. So I run this part of the code, I have a new DSA structure created, no delete variables. Of course I have more state variables because I'm working with a three-phase non-simplified MMC with not only circulating current control but also alternating current control, PQ control, among others, as well as a PLL in this version. Those are things that I can see in the equations file, which I have to open still. There we are. So this time I'm working with the three-phase MMC. I see that I have more parameters, that I have more states, that I have three-phase sets for the some capacitor voltages, upper arm, lower arm, and so on. I have also much more control variables. The algebra is a bit more complicated in the sense that now I account for Clark transformation. I have upper and lower arm current calculations. I have a positive and negative sequence extraction and so on. All of the details, also for the PLL, PQ control, and so on. All of the details you can find in the first chapter and the appendices of my PhD thesis. In this case, I do not include delays for this instance, so the modulation indices are equal to their references. The vector of differential equations is also longer. This time, for the definition of inputs as a function of time, I see that I have defined three-phase waveforms at fundamental frequency for the alternating voltage. I still have a constant value for the direct voltage. Then I have references for active power and reactive power. And I also have some time-varying parameters which are used in the PLL. I have made here some more elaborate structure to have several types of steps. If I leave the step type to 0, then nothing will happen. If I put it to 1, then I am adding negative sequence AC voltage at fundamental frequency. This is something that I see as I have these waveforms for the positive sequence, and I have this smaller amplitude multiplying a waveform for the negative sequence component. And lastly, I have defined a last type of step. It's an active power reference step, where on the mask I increase the value of the active power reference to 1.1. So those are the things you can do for time domain simulations. For collocation calculations, I have also defined the harmonic spectrum for the alternating voltages, direct voltage, active and reactive power references, as well as cosine and sines for the PLL. I also give an initial point, which an initial guess for the states. Clearly, I'm quite off for some of the values. What is important is that it is reasonably close to what you would expect. It doesn't have to be exactly that. Again, it is just an initial guess. In general, just being different from 0 will help the collocation method get started. In some cases, even starting from 0 may work perfectly fine. Just be careful about dividing by 0. So now what I can do with this three-phase system is naturally solve for the collocation methods. Let's do 2 mistakes directly to learn. So first we have a warning that this source is not available in the harmonic domain data. So an initialization from the last solution is not possible. Try setting initial guess from to user instead. For this particular run, the code will initialize the harmonic spectra from the user-defined HD file. So this is not a very important mistake, just the code will try something else. What happened is that I'm asking to solve with an initial guess defined from the solution, but I have no previous solution for this particular instance, which I have just created. And this is why we have this warning. And second mistake that has been done is that I have requested to work with an analytical Jacobian, whereas in the file here of my three-phase RMC, no Jacobian file has been created yet for the collocation method. So to solve this, well, either I put it to 1, so I reset the analytical Jacobian, or I could as well leave it to 0 and work with a numerical Jacobian. In the meantime, I will also start from the user-defined initial guess. I run it, and now it works fine. You see, this is a bigger system, and I'm not helping it a lot because I'm asking to work with a numerical Jacobian. Still, we do have the eigenvalues of the Jacobian since we are working with a non-delayed system, and I can show you that we're starting also from the user-defined data. Working with an analytical Jacobian is generally faster. So here, instead of taking 8.5 seconds with a numerical Jacobian, it has taken 2 seconds with an analytical Jacobian. And actually, things are even faster if you start from the previous solution, which it knows already, so it should go quite fast. There it goes. So 0.1 seconds to find again the same solution. But with this algorithm, just finding an even more accurate version with a smaller error. 10 to the minus 12 for the absolute residual error. This is really small.